chapter 22 is just taking things we've already learned about confidence intervals and hypothesis tests and errors and all that stuff. We're just doing a new type of interval and a new type of test when you have two proportions that you want to compare somehow. This is how I told you this is how the rest of the semester is going to go. We take one statistic and we learn about it, and then we take another statistic and we learn about it, and we take another statistic and we learn about it. So I feel like this shouldn't take too much effort because we've already done the basis of this. Like you already have pretty good base knowledge of what's going on, and then we're just going to kind of tweak it a little bit. All right? But since I graded your tests, you guys know how to do a hypothesis test. Excellent. You can get it, go through it. You got it. Great. But that either you didn't study for intervals or I don't know what happened because the intervals weren't as awesome. Okay? So since we're talking about intervals today, I want to make sure we know what we're talking about from chapter 19 first. So in a confidence interval, every single confidence interval we will do in this entire class always follows the same pattern. Always. It's what it says on the AP formula sheet. It says statistic plus or minus critical value times the standard deviation of the statistic. Right, that's what it says on the yellow sheet, AP formula sheet. You have to know what those things are so that you can plug everything in so that you can get the right answer. Now, in chapter 19 and 20 and 18, all those chapters, 18, 19, 20, we were talking about one proportion, and so there were statistics and parameters. And I mentioned this before, too. It's a matter of vocabulary. So we had one proportion, and so our statistic is p hat, and our parameter is p. Right? What's the difference between those two? What's the difference between p hat and p? P hat is based on your sample, like a survey or experiment or something that you did, and p is what you think is happening in the population, right? Okay, so if you're doing a confidence interval, it says statistic. So in chapter 19, our statistic would have been p hat, right? Now on the free response question, they give you a lot of percentages. They gave you a p hat. They also gave you a p. So which one should you have used in the confidence interval? P hat. All right, a lot of you guys didn't. Use p. That's fine. You're going to lose credit for that, but at least you did the mechanics and things. But you should use p hat. All right, plus or minus our critical value. In this case, what is the only critical value we have talked about? Z. And some of you guys still don't know how to find those. And then we have the equation from the formula sheet as well for the standard deviation. P hat, Q hat over n square root of that. Right? That was the formula. You only had one to memorize at that point, and some of you guys didn't do that great and awesome with it. Now I'm going to add another one. So you really have to start relying on knowing what those words mean so you know what to put into the formula sheet. Okay? Now some of you guys still don't know how to figure out what Z is. That's a problem. So let's say I want to be 88% confident. Then how do I find that critical value? You do put it in the calculator, but what do you put in the calculator? Inverse norm, that's good. So I'm going to be 88% confident, so what am I going to put into the calculator? 0.06, right? You're worried about the middle 88%, if you will. And so that means there's 12% left over, and so there's 6% on each side. And you're looking for these two values, right? So if you use inverse norm and put in 0.06, it's going to give you this one. And then there would be a positive version over here. That's why there's a plus minus. Okay? Yeah? Okay. Good. We're going to be using all of these things today. Now, that's the mechanics of it, but what are really essentially the 3 steps to a confidence interval? There's like 4 steps to a hypothesis test. What are the 3 steps to a confidence interval? What's the first thing you should do? Check the conditions. So that's not changing. We're still going to check the conditions. After you check the conditions, you actually do the math, right? You show the math, you do the interval. put your intervals in order. I'm not going to ask anymore. I'm going to start taking off points because you put them backwards. It doesn't make any sense. Because then you write me a sentence and you're like, I'm 95% confident that the true proportion of people wearing black t-shirts today is between 13% and 5%. What?
I'm so guilty of that. Because I'm just working on my earlier.
It doesn't make sense. That's great, but it doesn't make sense. No. No. So, after you do the mechanics, you write me a sentence and you tell me you interpret the interval. Some of you guys didn't do that on the free response. Like you did the math, and you got the interval, and it was beautiful, and then you didn't write the sentence. I'm blank % confident that blah, 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 right? They're not going to ask you to do that. It's part of the confidence interval. You have to interpret what the interval means. Okay? Questions about those steps? So we're going to use those steps today. Now, we're going to do two things today. We're going to talk about the sampling distribution model that confidence intervals and hypothesis tests are based on for two proportions. And then we'll talk about the actual confidence interval. Now, when I say comparing two proportions, that means we have like two groups. And we want to somehow see how they are related. And we're always going to see how they're related by finding a difference between the two. We can see how far apart those percentages are. So we said the first thing we do whenever we do a hypothesis test or a confidence interval, even talk about sampling distribution model, is check the conditions. The conditions are the same, but listen very carefully. I'm going to make up an example. I used it this morning. It worked out fine. Let's say on Friday, last Friday, I took a sample from Murray High School and from Callaway County High School about the proportion of students that are wearing sneakers. All right? Or tennis shoes to school. All right? So I want to see if there is how different those two are. Okay? If I'm going to do a hypothesis test or a confidence interval or anything, I have to check the conditions about that. So the independence assumption, you have to assume not only that the Murray students are independent of each other, but also that the Callaway County students are independent of each other, right? It's almost like you're checking the conditions twice. You have to do this for both groups. The randomization condition, same thing. Random sample from Murray High School, random sample from Callaway County High School. Yeah, you can just say it all in one sentence, but you need to say both of them were randomly sampled. 10% condition, the sample size of the Murray sample was less than 10% of all Murray High students. The sample size of Callaway County was less than 10% of all Callaway County High School students, because they don't have to be the same sample size. I could have sampled 30 people from Murray High School and 125 from Callaway County High School. It doesn't really matter. You have two samples. Make sure you meet the conditions. The one thing I'll add into independence, we have to add in independent groups. So not only do I need to say in that first part that I'm assuming that all the students at Murray High are independent of each other, and I'm assuming all the students from Callaway County High School are independent of each other, I then need to say that the students at Murray High School and the students at Callaway County High School are independent of each other. Okay, so you're independent within the group, and the groups are independent. Does that make sense? So I'm adding a condition. Everyone go with that. The other condition is still sample size. It still exists, right? Success, failure. We do NP and NQ. Are they greater than 10? You should do it twice. Because you'll have two different proportions, one for each group. You'll probably have two different sample sizes, one for each group. So you do NP and NQ for the Murray High School students and NP and NQ for the Callaway County High School students, and show that those success failure rate is, or both of those are greater than 10. The number of successes, number of failures. So the conditions are the same. You should check more in detail because you have two separate groups to think about. Is everyone okay with that notion? Yeah? All right. I said that. Okay. So a confidence interval and a hypothesis test are both based on a sampling distribution model, which is in chapter 18. In a sampling distribution model, we check the conditions, and then we came up with what the mean and standard deviation would be for our model, and we could draw it, and we could like find probabilities if we needed to, without actually having to do an interval or a test or anything. So same thing here. So in chapter 18, think back, chapter 18. If we were going to talk about a proportion, we expected the mean of the model to be whatever the proportion was that they gave us, right? So if I said that 30% of Murray High School students wore sneakers on Friday, then the mean of my model would be 30%, because I expect the same thing to be happening with the population with my model, okay? In this case, again, we're talking about comparing two groups, and so when we compare the groups, we find the difference, because that way we can see how different, like how much space is in between the two percentages. So our mean is just going to be one proportion minus another. Okay? Okay. Then we had an equation for standard deviation we've been using, the square root of PQ over N, right? So we have a standard deviation equation now for the difference in two proportions. It's on the yellow formula sheet and the AP formula sheet, so no worries. But just to see how much you remember, why is there a plus sign there if we're subtracting the proportions of the mean? Because of the variance idea, right? Way back before Christmas, you can't just combine two groups, you had to add, right? Add variances. All of that stuff has been taken into account to write this formula. That's why there's a plus sign. Again, I would reference the formula sheet instead of trying to memorize everything and then getting it wrong. Just take 5 seconds to look at it before you actually write everything out. Okay? You guys are doing a better job of writing all of your numbers out in the formulas, and I'm finding that you're writing them correctly, and then you're making a calculator mistake, and so I'm not having to take as many points off because I can figure out what you did. All right? So again, that's why I'm telling you to show your work, not because I just am trying to torture you, but because on a free response question, if you write it all out, and then you have the wrong number, they're not going to take points off for that, and they're going to do the entire problem with your numbers instead of the numbers on the rubric to make sure that you had the right idea. Questions so far? All right, so let's do an example with that. Just about sampling distribution models. A presidential candidate fears he has a problem with women voters. His campaign staff plans to run a poll to assess the situation. They'll randomly sample 300 men and 300 women, asking if they have a favorable impression of the candidate. Obviously, the staff can't know this, but suppose the candidate has a positive image with 59% of males, but with only 53% of females. So again, this isn't a confidence interval. These are sample proportions. These are actual proportions. They're just telling us what they are. So a good review question here, part A. What sampling design is his staff planning to use? So like way back in chapter 12, what type of survey design is this? $300 men and 300 women. Stratified. Thank you. That's the word. It was in there. But yeah, so so stratified. They were going to sample a little bit of each group, right? Okay. On B, non-trick question. What difference would you expect the poll to show? Again, they haven't done the poll. These are the actual numbers for the population. We're pretending we knew those, all right, to answer these questions. So if this is what's actually happening in the population, then what difference do you expect to see in the poll? What difference is there? It's not a trick question. 6%. So we expect to see a 6% difference. That's going to be the mean of our model, right? C, of course, sampling error means the poll won't reflect the difference perfectly. So what's the standard deviation for the difference in the proportion? So we use that formula that we just talked about. We have to do men and women. So we have 59% and 41% over 300. 53%, 47% over 300. And I'm not going to type all this in. I'm going to cheat and look up the answer. about 0.0405. Be careful. Some of you guys are just typing things in your calculator weird. If you need to do it in pieces, do it in pieces so you don't mess it up. Some of you guys like to take the square root at the end, that kind of thing. Just take your time. Any questions about where that standard deviation came from or where any of those numbers came from that I put in that equation? Okay. D says then sketch a sampling model for the size difference in the proportions of men and women with favorable impressions of this candidate that might appear in a poll like this. So if we're going to sketch the model, we know it's a normal model. We expected the difference to be 6% with a standard deviation of about 4%, right? And then if we were going to label this, this would be the difference in proportions of men and women with a favorable impression of the candidate. Right? Way to label it. There we go. There's our model. Now, I could, at this point, if they ask me a probability question, I can answer it. If they said, what's the probability that the difference is actually greater than 15%? What was greater than 15%, then I would want to know what this probability is up here, and I could use normal CDF to figure that out. Right? So that's where sampling distribution models can be helpful. We can find probabilities. Now, the question actually asks, in part E, could the campaign be misled by the poll, concluding that there really is no gender gap? It's a weird question. This again is a sampling distribution model. This is showing you that like 68% of poll results would fall within here, right? 95, 99.7, right? You have your standard deviation. If there was no gender gap, what would the difference be? Not a trick question. If there's no gender gap, what would the difference be? 0, which is right here. Okay? 0 is how many standard deviations below the mean? Like 1.5. Like 1.5. Is 1.5 standard deviations below the mean unusual? No. So here's where this question gets tricky if you don't read it right. So that's not unusual to get 0. So 0 could be a possible poll result, right? Like this model represents possible poll differences. So 0 is a possibility if they did this poll. Does that make sense? The question says, could the campaign be misled by the poll, concluding there really is no gender gap? Well, yes. Right? We know that there is a gender gap because these are the true population percentages, right? They're talking about what's going to happen in this poll. Well, 0 is feasible because only 1.5 standard deviations below the mean. It's not unusual. So yes, they could be misled. They could easily get 0 as a result and be misled and think, oh, it's fine, right? In real life, if we were going to do a poll, we wouldn't know these numbers. So we would make a conclusion, oh, there's no gender gap, and move on about our business, right? In this problem, we just happen to know these numbers. Questions about that? All right. Then let's talk about confidence intervals. So these are called two proportion Z intervals. Very fancy. Two proportion Z intervals. Make sure you're talking about an interval when you're going to do an interval and a test when you're going to do a test. On the free response question on the test, you're supposed to do an interval. And you guys told me you were going to do a test. But then you did an interval. So make sure you say the right thing. So, we have a two proportion Z interval. If you look at it, it follows that same pattern I wrote at the beginning of class. Statistic. In this case, we're talking about two proportions. So the statistic is the difference in the two p-hats. All right? plus or minus z star. That has not changed. The critical value is the exact same when you have one proportion for when it has two proportions. So if I ask you to be 95% confident, what number are you going to use? 1.96 still, because it's not changing. Okay? And then times the standard error or the standard deviation of the statistic, which is that new equation we just came up with. And since it's an estimate based on p hat and q hat, it's a standard error and not a standard deviation. Right? But does this not follow the exact same pattern we talked about at the beginning? Yes. I'm going to keep adding intervals from chapter to chapter. Again, you have to get good at using that sentence to be able to figure out what you're supposed to do instead of memorizing a bunch of different formulas. Any questions about that? Now, since you're doing a difference, you can choose whichever group you want to be 1 and whatever group you want to be 2. In my personal opinion, I would rather things be positive because that makes my life easier and makes the interval make more sense. So generally, if I'm going to set up a confidence interval, I'm going to set it up so that the difference is positive. Setting up the difference as negative is not wrong. You should think about the conclusion backwards. Okay? If you have a difference that's negative, you'll get an interval with negative percentages, which doesn't make as much sense. But that's why I have to think about it a little bit more, so that's why I would make it positive. It's not wrong if you do it the other way. All right. So can we do an example? The Centers for Disease Control and Prevention reported a survey of randomly selected Americans aged 65 and older, which found that 411 out of 1,012 men and 535 out of 1,062 women suffered from some form of arthritis. So this is going to go through, and A, B, and C are going to split this all up very nicely for you in the 3 steps, but generally it's just going to say construct a confidence interval, and you're supposed to do all 3 of these things anyway. So our book is trying to be nice, but remember these are all 3 parts of this. So A, are the assumptions and conditions necessary for inference satisfied? Do I have to write them all down, or can we just talk about them? Excellent. Here we go. Independence. 1,012 men are independent of each other. We can assume that 1,062 women are independent of each other. And we're going to assume that the men and the women are independent of each other. Right? That was the new part, independent groups. So I said 3 things right there. It doesn't have to be like this big, long paragraph. You can just write quick sentences, but make sure you hit all 3 of those things. Did you hear me? You don't have to write a full paragraph, 3 quick sentences. Just checking. All right, randomization. It says that the men and women were randomly selected, right? So both the men and the women were randomly selected. Make sure you mention both. Again, don't just write random sample check mark. Yes. People don't listen to me. I tell them what to do, and they do the opposite. All right, 10%. 1,012 men is less than 10% of all men age 65 and older. 1,062 women is less than 10% of women age 65 and older. You gotta say both. Okay? And then the last one is success failure. Now, for success failure, you need to know what P is. So you have 2. You have P hat for the men, and you have P hat for the women. So you do 411 out of 1,012, and you get 0.406. And 535 out of 1,062, you get 0.504. Right? So I would need to do 0.406 times 1,012. Is that greater than 10? Definitely, probably. Right? And then you would do the complement. So 1,012 times the complement of 0.406. Or they give these to you as counts. Right? They tell you 411 of them have arthritis. So you could just write 411 and then subtract 411 from 1,012 to get the number of failures. Does that make sense? You don't have to multiply if you already have the counts given to you. Same thing for the women. You could do 0.504 times 1,062 and then the complement times 1,062. Or they give it to you as counts. So you could just say 535 is greater than 10. And then 1,062 minus 535 is 527. Okay, so you can multiply or you can look at the counts. Regardless, you have to show me that success failure is achieved for both groups. Everyone okay with the conditions? So just make sure you indicate you're talking about both groups on each of those conditions. Then you need to write a sentence. It's getting more and more crucial you write this sentence because I'm adding more types of intervals and tests. So you have to identify what you're doing. Because the conditions are met. I can use a normal model for the sampling distribution for the difference in proportions. That's what you should say. You're not going to say that part. And so then you're going to definitely name the test though. So I can construct a 2 proportion Z interval. Right? Write the sentence. Okay. Part B says to create a 95% confidence interval for the difference in the proportions of senior men and women who have this disease. So we're going to follow this formula, right? Or you can follow what it says in the formula sheet. Statistic, plus or minus, critical value times standard deviation of the statistic. So in the example, would you rather do women minus men or men minus women? Women minus men, because that way we get a positive result. It's not wrong to do the other way, but I'm going to do it positive. So 504 minus 0.406, that's our p hat 1 minus p hat 2. Plus or minus, we're being 95% confident, so the Z critical value hasn't changed. It's still 1.96. And then we're going to fill in that standard error equation, right? So we have 0.504 times 0.496 out of 1,062. Be careful you have the right sample sizes. 406.594. We're in our room, leave me alone. 1,012. It's fine. It's all good. Okay, again, make sure you're writing that out so that if you do make a calculation mistake, you had it set up, you're probably going to get full credit on a free response for that. Okay. So we end up getting 0.098 plus or minus 1.96 times 0.0218. It's not consistent, so I'm not going to say that all of you guys do this all the time, but I see it enough that I'm concerned. When you're doing these, make sure you follow the order of operations. It's like some people make the mistake, but then the next time they don't make the mistake. So, again, it's not consistent. I'm just going to throw that out to the universe. Like, don't add 0.098 to 1.96 and then multiply. Okay. So 0.098 plus or minus 0.0427, and we get 0.055 to 141. Look, see, it's in order. Okay. I'm being sassy because I'm over it. It's backwards. It doesn't make any sense. All right, so we have found the interval. Questions on how to do the math? Follows the same pattern, right? All right, so then C says interpret your interval in this context. Now, here's the deal. You can use this general template that I gave you before, and I'll go ahead and write the conclusion that way. But then I'm going to write the conclusion in a different way that sort of makes more sense. They're both correct, but we're comparing two things. So the second statement is going to make more sense, but we'll go with the first one we know for now. Normally we would say I am 95% confident that the true proportion now in this case we're talking about difference in proportions, right? So the true difference in proportions of women and men suffering from arthritis is between 5.5% and 14.1%. That's not wrong. Right? I'm 95% confident that the difference in proportions is somewhere in that interval. Right? Here is another way to say that, though. We did women minus men, right? And we have an interval that has two positive numbers. So women minus men, that means that this difference is positive. That means that the arthritis has a higher percentage in women than men. Does that make sense? So another way to write this is, I am 95% confident that the proportion of women suffering from arthritis is 5.5% to 14.1% higher than the proportion of men suffering from arthritis. So the second statement makes it more comparative. Right? One group is suffering more than another by this much. Does that make sense? Now, if you had done the interval differently, this is where I said it takes a minute to flip things around in your head. If you'd done men minus women, you would have gotten the same numbers, they'd just been negative. So your interval would have been from negative 14.1% to negative 5.5%. All right, all that means is that you're 95% confident the proportion of men suffering is that percent to that percent less than women suffering, right? It takes you kind of like flipping it around in your head. The second statement is better because it's directly comparative, whereas the first statement is just kind of like going through the motions, and we just say that the difference is in this interval. They're both correct. Now, part D, whenever we do a confidence interval, we're generally trying to ask some sort of question with it. Or does something fall in that interval, right? If it falls in the interval, then something's not unusual. If it doesn't fall in the interval, then maybe something's happened. Well, so part D says, does this confidence interval suggest that arthritis is more likely to afflict women than men, and explain? When you're looking at these difference in proportion questions, there is always a difference in the two groups if 0 is not in your interval. If 0% is in your interval, then there's a possibility there is 0 difference, right? So you're always looking to see if 0 is in the interval or not. If it's not in the interval, there's probably a difference in the two groups. So is 0% in my interval? No. Our interval is entirely above 0. So does that support that arthritis is more likely to afflict women than men? Yes, it does. Right? Because 0 is not an interval, there isn't a difference in the groups. And we already said that more women are affected than men. Right? We said it's 5.5 to 14.1% higher than men. So yes. Now if it does contain 0, we would say there's not a difference. 0 is a possible value for the true difference in proportions. So there could not be a difference. So you're always looking to see if 0 falls in the interval or not. Questions about that? Okay.